everyone. We're going to work on some examples from adding and subtracting radical expressions. So remember, the core principle that's guiding us whenever we're doing addition subtraction is you can only count things up, you can only add them up or subtract them if they are the same thing. So we need like terms. So the first one, just to get us going, is a reminder of what that looks like for radicals. The things that we're adding up are the root 7s in this problem. So if I have 3 root 7s and I take away 5 root 7s, I have -2 of those root 7s. So this is, I think, probably fairly straightforward at this point. Where it gets tricky is when you don't initially have like terms, but it's possible to simplify the roots. So you want to be watching always for roots that can simplify that might become like terms. For example, in number 2, we can split that cube root up and say, okay, I need the cube root of 8 times the cube root of pi plus the cube root of pi. And 8 is a perfect cube, so I can say, well, that's 2 cube root of pi plus cube root of pi. So if I have 2 cube roots pi and I add one more of them, I'm going to have 3 cube roots of pi. Okay, so that's kind of like having a variable in the mix, but technically it's just numbers. So let's do one that truly has variables in the mix. So again, looking at this one, it's getting a little messier. I have 8 times the square root of 2p cubed minus 3p times the square root of 18p. Definitely not like terms right now. The square root 2p cubed is not the same as the square root 18p, so we're looking for that radical part to match up, but we also need the variables to match up, right? So it's the only thing that doesn't need to match is the coefficient, the number all the way out in front. That's the number that's telling us how many we have. Everything else is part of our like terms business. So let's see, I am going to try and simplify roots. What I'm seeing is that under this first root, I could say that's 2 times p squared. 2 doesn't have much to work with in the way of factors, but p cubed does give me enough p's that I could split 2 of them off and say that's the square root of p squared multiplied by the square root of 2p. The second one, I only have a single p, but I can split the 18 into 9 times 2. And I'm going to split off the square root of 9, and I'll be left with the square root of 2p. So this is looking promising because they both have that root 2p. So when I take the square root of p squared, I get 8p root 2p. And when I take the square root of 9, I get a 3. Remember, this is all multiply over here, so I can go 3 times 3 is 9. P square root 2p. So now my coefficients are 8 and 9. Those don't have to match, but everything else does. And I'm in luck because p root 2p does match. So the things I'm adding up are p root 2p's. And I have 8 of them, and I take 9 away. So my final answer is going to be I have -1 of them. Okay, so that's my answer. So in some ways, addition and subtraction here is nice because once you make those radicals match, you're in good shape, but they can start to look a little weird when there's variables under the root, variables out in front of the root, and keeping track of what has to match. Basically everything but the coefficient, right? Okay, so let's do another. Not too long on this one yet. Okay, so 2 variables in the mix. We're making this look really ugly. So same idea here. I need everything to match. The radical part has to match. The variables out in front have to match. The only thing that doesn't have to match is coefficients. And right now the coefficients are all 1, so that's kind of boring. But the radicals and the variables are lacking. So it's very easy to make up something like this where it's not all going to match, and then you would just quit. If they aren't the same, exactly the same, you don't count them up. But of course, you should see some nice ones in your homework where they do work out nicely. So I'm going to say here I have 100 times 3, and the x's, I can say I have an x squared times x. So I can separate out a square root of 100 and a square root of x squared, and I'm going to be left with the 3, the x, and the y. From the second one, I'm looking for perfect squares. Don't be tricked by the 27. It's a perfect cube, but it does have a factor of 9 in it. The x is just an x. I can't do anything with that, but the y's, I can split off 4 of them. So I can say, okay, this is minus x, square root of 9, square root of y to the 4th, and then I'm stuck with a square root of 3, the x that's left under there, and that lonely y. This is looking good so far with the root 3xy's matching. The last one, xy squared, I can't get any x's or y's out of the roots, but I can say that's 4 times 3 and split off a root 4. And I'll be left with a 3, an x, and a y. So I'm really liking this radical part matching up. That's a good sign. When I start taking roots, the first one's going to give me a 10. Oh, sorry for the yawns. X, y squared, square root 3xy. For the second one, I'm going to get a 9x. The square root of y to the 4th, remember that's like y to the 4th to the 1/2. When you multiply that, you get y squared. Really looking good. The variables out in front and the radicals match. Last one, the square root of 4 is 2. And I kind of deliberately am alphabetizing my variables just so that I don't accidentally trick myself and look at an xy and a yx and think they're different. They are not different. So I now have 10 of these xy squared root 3xy's, and I'm taking away 3 of these xy squared root 3xy's, and then I'm adding 2 xy squared root 3xy's. So 10 minus 3 is 7, add 2 back in, I end up with 9 xy squared square root 3xy's. So again, you got to train yourself to kind of mentally block together all this variable mess and just say that's your apples, right? I have 10 apples, I subtract 3 apples, I add 2 apples. As long as you're not trying to add oranges to apples, you're in good shape. Okay, we're going to make this one a little bit of a longer one since there's only one example left and just do them all in one video. Zoom a little. This one only has one variable in the mix, so in that way it's simpler than the last one, but it is cube root, so we have to be a little bit careful about those. I have a 6q squared times the cube root, those powers line up kind of strangely, of 5q. There are no perfect cubes under that root, so this one I can't do anything about. So I better hope that I can get a q squared cube root 5q out of the second one. And again, this lined up kind of funny, but this is supposed to be a q to the 1 times the cube root. So here I can separate out some perfect cubes. Remember, for numbers, you'd be looking for 8 or 27 or 64. 8 works for this one. For variables, you're looking for any set of 3, right? Or multiple of 3 works as well. So I can split off a q cubed. So when I'm done, I'm going to have a plus 2q times the cube root of 8 times the cube root of q cubed. That's a tongue twister. And I'll be left with a cube root of 5q. Okay, so looking good on the cube root of 5q part. So I have a 6q squared cube root of 5q. And then cube root of 8 is 2. So when I multiply that in, remember they're all multiplied, I'm going to get 4 out in front. The cube root of q cubed is just a q. So I'm going to have a q out in front times another q, which is a q squared. And then the root 5q, cube root 5q. So the only thing that doesn't have to match is the coefficient. So here's my apples, and these are also apples. Q squared, cube root 5q's are what we're adding up. We have 6 of them. We add 4 of them. We're going to end up with 10q squared cube root 5q's. Okay, so hopefully that gets you going on adding, subtracting radicals. Thanks for watching.